Okay. Good. Right. Can I start?
Yes.
Okay. So hi everybody. It's a great pleasure to be here today, and thank you everyone for the invitation. And today I'm gonna talk to you about some of my research topics that involve softwarization and openness for NextG cellular networks. Okay. So during this presentation, I will cover some basic background. So why we need a new architecture for next generation cellular networks. Then I will go through some approaches to implement data-driven and control loops operation in the Open RAN with some specific focus on the ORAN architecture. I will also talk to you about the zero-touch optimization of softwarized cellular networks. And finally, we'll conclude with some remarks on prototyping for NextG at a scale. So why do we need a new architecture for 5G? So 5G and beyond cellular networks are envisioned to support many new applications with diverse requirements. So we may have some applications that require high throughput, so enhanced mobile broadband applications. We might have some applications that require very low latency. So for instance, think about autonomous cars applications, where you might have a very low latency between your action and the actual control. So for instance, if you hit the brake, you don't want the brakes to start braking too late. Or you might have other applications like for cyber physical systems in the IoT. Also, all of these requires flexible and programmable architecture, and there is not really a one-size-fits-all solution. So you cannot have a single solution to address all of these, but you need to have some adaptive solution that is able to dynamically react based on your use cases and environment. So also another thing that is happening in next generation cellular networks is that the complexity of the network is increasing. So we have more and more network devices. So we can have cellular networks with serving actual cell phones. Or we can also have drones that are users. So we not only have cellular phones, but also drones that are served by a base station. Or more recently, we can also have some VR and AR, so virtual reality and augmented reality devices that need to be served by the cellular network. But also, we need more spectrum. So basically, the current situation with the spectrum is that most of the spectrum is currently used, so at least sub-6 gigahertz spectrum. And now people are exploring new portion of the spectrum, such as millimeter waves communications, or also in the terahertz bandwidth. So all of these to say that with the increasing of devices and evolution of the technology, we also need more spectrum to serve all the users of the network. And also, we have newer protocol stacks to answer all these requirements, but these protocol stacks become more evolved and more complex. So we actually need a novel architecture to be able to interact with them and to answer all of these requirements that the network has. Another thing that we need is an automated and intelligent architecture. So the network should be able to autonomously react to what's going on around the network. So for instance, the increase of the traffic demand or the different conditions of the network, or maybe even the requirement of new services that are required on demand from network operator. And all of these needs both an automated way to orchestrate things and also an intelligent way to, for instance, optimize some goal of the network. So the traditional network architecture that we had pretty much so far was formed by a black box approach, where you had some equipment sold to the operators from specific manufacturers, and this equipment might be a cellular base station that is sold by operators like Nokia or Ericsson. So this kind of equipment is called black box because you, or let's say the operator, cannot really fine tune and control what's going on into the specific piece of equipment. So if you think of a base station, they may be able to tune some of the parameters like the operational frequency of the base station, but they cannot really access the lower level capabilities of the base station to adapt its functionalities to their own needs. So for instance, the operator cannot go inside the base station and program a different scheduling algorithm to serve the users in a more intelligent or in a better way, let's say, or they cannot implement some optimization algorithm to achieve some high level control of the network. So for instance, to maximize the throughput of premium users. But they can only use this base station as a black box, so feeding some packets to the equipment or the base station, and the base station will produce something like, for instance, will transmit this packet, but without any intelligent embedded. So we have this limited reconfigurability and adaptability of the equipment, and of course, with this also comes the difficulty in coordinating multiple nodes of the network. So you cannot really program any coordination that has not been baked into the specific piece of equipment by the manufacturer, meaning that this also implies that when the protocols evolve, you cannot modify your actual base station without the need to buy a new base station from the manufacturer. So there's this slowdown evolution and between the actual stack evolution, the actual evolution of the 3GPP stack, and the need for a new piece of equipment bought by the network operator to deploy in the actual network. And with all of these also comes vendor lock-in. So the architecture cellular networks have been used so far with this black box approach have this problem that is very significant, and it means that you cannot purchase one piece of equipment from a manufacturer and then purchase another piece of equipment from another manufacturer and have the two of them interacting with one another. So this means that if an operator bought all the equipment from manufacturer A and design all the network based on this equipment, and then tomorrow manufacturer B produces a new piece of equipment, so a new base station, the operator cannot just simply go to manufacturer B and buy a new piece of equipment, so the new base station, and integrate this new base station in the network and make it working together to the other base station from manufacturer A, because these two are simply not designed to talk to one another and they will not work together. So the operator is actually locked into the configuration of the network, and this configuration cannot be easily changed without changing the whole network equipment and infrastructure. So the way that we're evolving right now, that cellular networks are evolving, is toward an open programmable architecture, where you have some open interfaces that constitute the openness of this open and programmable architecture. And through these open interfaces, the various pieces of equipment, so for instance, the base stations I was mentioning earlier, can interact to one another by using these open interfaces that have been standardized and that all manufacturers should implement in their equipment. So these interfaces actually allow pieces from multiple vendors to interact to one another. So an operator can first buy a piece of equipment from manufacturer A, and then tomorrow a new piece of equipment comes out and from manufacturer B, and they can integrate this piece of equipment in the existing network without the need of changing the whole architecture and the whole equipment. And this is done through these open interfaces. For instance, the F1 interfaces between cellular CUs and DUs, and the open fronthaul interface that connects the DUs and the RUs. And the openness is also two-sided. So one side is this open interface, so the openness of the interfaces. The other side is the openness of the actual equipment, in the sense that you can access the equipment and program the equipment through open source cellular stacks, and you can instantiate an open source stack, an open source program on your equipment that actually implements all the functionalities of the base station. So if you want to implement a new scheduling algorithm, and this is the example I was mentioning before, you can access the equipment, you can access the code of the base station, and you can program your scheduling algorithm to the base station, or maybe the optimization algorithm to optimize some specific need that you might have. So for instance, to serve higher throughput to premium users. And all of this is possible because these services, so these base station applications, or even the core network application of the cellular network, can be seen as services that are instantiated on demand or virtualized on general purpose infrastructure. So the architecture will be that you have data centers with many general purpose servers. So you have some machines that can potentially do any role in your network, and you are the ones that decide that you want to instantiate a specific application on a certain server. So for instance, you decide that on the first server you want to instantiate the core of your network, while on the second server you might want to instantiate the base station application of your network. So you don't have any more specialized piece of equipment, but you have several general purpose machines or servers where you can actually instantiate your applications based on your needs. So in this picture, you see the CUs and DUs, and these are the distributed unit and cellular and centralized unit of the cellular network, and they can both run on general purpose devices that are not specialized in any way to accomplish a specific role in the network, but they can perform several tasks based on the needs of the operator at a specific time. So in this way, we have some networks that we can also program to achieve some specific goals. So we can optimize some metrics, and we can implement control loops between our intelligence, so where our intelligent applications run. So think about machine learning or optimization applications that have to achieve some goal in your network, and you can implement some loops where you have your network sending some metrics and statistics about the operation of the network to these applications that run the intelligence, and then they send back some control action that the network should perform. So also another side of this change is that in the traditional architecture, where you have a black box architecture, if you have an operator's intent, so the operator's to suddenly achieve some specific goal in the network. So in this example, the operator wants to transmit a 4K video to 100 users in Times Square, New York, at a certain time of the day. In the traditional approach, you really need manual reconfiguration. So you need to send some engineering team to the actual site and to program some ad hoc solution to achieve this goal. And this, of course, results in a need for the people who go on site, the manual reconfiguration of the infrastructure, and some high cost maintenance. And this, although this might be feasible if you only have 1 or 2 base stations, think about operators that have thousands of base stations. So this is hardly feasible in that case, and this also leads to poor performance because such solutions wouldn't be able to adapt to the network requirements. However, in this novel approach that we're envisioning, the operator intent can be just passed to some centralized controller of the network or distributed controller of the network. So you can think about some application that has a global view of your network, or a view of a certain pieces of your network that can receive this high-level intent. So for instance, the need of the operator to stream a 4K video to 100 users in Times Square, New York. And this piece of equipment running the intelligence of your network will be able to automatically convert this intent at a high level from the operator to an automatic solution that will be deploy the actual services. So for example, the base stations required to achieve this intent will be deployed on a general purpose machine. And they will be able also to adapt to the network traffic demand requirement by implementing some optimization control, and with the final goal of improving the performance of the network with this called zero-touch reconfiguration, because really at this point, the operator just needs to implement to express an high-level intent, and that they don't need to touch anything else. So it's a zero touch, and the network reconfigures itself. So in one of the works I've been working on, we implemented data-driven control for O-RAN networks. So the O-RAN architecture allows you to implement different control loops through the so-called RAN intelligent controller, or RICs. So we have, for example, no real-time control loops that address operations with time scales higher than 1 second. And this may be the orchestration of your network resources, so your actual base station application or core network application, or CU and DUs, to talk with a 3GPP jargon, let's say. And these decisions that are made at no real time impact on thousands of devices. So you can think of it as a hierarchical architecture where at the top you have no real time control loops. And examples of these actions can be the tuning of slicing algorithms, or selection of machine learning models to run on the network to optimize the network performance. Another kind of loops that is envisioned in O-RAN is what is called near real-time loops. So these loops cover operations with time requirements between 10 milliseconds and 1 second, and they actually allow you to run the intelligence in the network through third-party applications that we will see shortly. And some of these operations can act on the inference or classification routines of the network. And they also can do traffic prediction or decide the scheduling policy that a certain DU should run, or the specific allocation of RAN slicing resources to the network. Then there is another set of loops. So we've seen no real time, near real time, and now there are also real-time control loops, and these loops are with time scales lower than 10 milliseconds. And examples of these are scheduling the actual resources of the DU, or the interactions between the DU, so the distributed unit, DRU, that is the radio units, and the users of your network, and for tuning of modulation and interference detection. But however, as of now, these control loops or real-time control loops are not currently addressed by the ORAN specifications, although they might be at a later stage of these very same specifications. A use case for this kind of applications might be to schedule the RAN slicing resources in an intelligent way. So you want these slicing resources and scheduling resources to adapt to what's going on in your network. And however, this is not simple, and this might be challenging because you have the dynamicity of the wireless channel. So based on how many users you have, what's going on, if the users are moving, reflections, diffractions of the environment, so on and so forth. The ways this is implemented need to be mindful of all these effects and to be able to adapt to these varying dynamics. And also, you need to have a dynamic resource allocation for each slice of your network. So when I was talking before that there is no solution that fits all, in this case, you might have different services running on your base station. So you need to be mindful of each service, because what is good for one of the services, like for an EMBB service where you need to have a high throughput, but you might tolerate some latency, might not be good for a ultra reliable low latency communication where your primary focus is to serve users with the lowest latency possible. So all the solutions need to be able to adapt to such dynamic conditions, but also the different services that you might run. So this can be done. So one of the ways to do this is through the implementation of data-driven closed loop control through the near real-time run intelligent controller, or RIC, and to automatically tune the dynamics of the RAM based on the requirements of the operator. And we've been doing that through the use of XApps. So XApps are some external applications that can run on the near real-time run intelligent controller specified by ORAN. And these XApps are just external application that the operator can program to implement their own intelligence. And then these XApps can connect to the other components of the near real-time RIC, and then can send control actions to the actual run. So for instance, to the base stations, while at the same time receiving the network statistics they need to actually make the decisions intelligently. So you might think of a base station that is serving some users, and the base station periodically collects data of the network and sends this data to the XApp that is running on the near real-time RIC. At that point, the XApp will look at the data to figure out what's going on in the network, and it will tune the decision accordingly. Examples of these might be to change the scheduling policy that is running for a specific slice of the base station, or also we've tested the resizing of the slicing allocation for each base station. So we run in this example 3 different services on 3 slices. So we run a enhanced mobile broadband service that requires high throughput, and then we also have a ultra reliable low latency service, and that requires lower latency, and a machine-to-machine communication type of service. And the actions we've been exploring are to change the scheduling algorithm and to resize the spectrum, the portion of the spectrum, so the size of the slice that each one of these services has allocated to themselves. And however, this is not trivial, because ORAN mandates that you can only deploy machine learning models that have been trained a priori. So you can only deploy a model on the infrastructure after you train and validated the model. And this is done because, especially at the initial stages, machine learning models can make decisions that are random, and they might severely impact the performance of the network. So if you have a poorly designed application that runs on a production network, this application might have actions that might take actions that can destroy the operations of the network, or you might have outages on the network that translate in a loss of money from the telecom operator. So I mentioned that the only pre-trained models can be deployed, but I should also mention that if you deploy a pre-trained model, you can still fine-tune the model on the production network through online learning. But the model you deploy initially needs to be stable enough not to cause outages or not to destroy the operation of the network. Once you do that, you can still refine the model through online learning. So based on the actual data that the cellular network is sending, or the traffic condition that is experiencing at that specific time when the model is actually executed on your network. Also, another thing is that when you do the offline training, you need to be able to train your machine learning solution on very different scenarios, because your solution will be deployed on very many different actual deployments in the production infrastructure. So think, for instance, of a urban deployment or a rural deployment. So you need to be sure that your solution performs well in both these cases. And this means that you cannot simply just train your solution in a urban deployment, and then you do this training offline and you deploy your machine learning application on a rural deployment on the actual infrastructure, because this application might not work. So when you do the offline training, you also need to be sure that you are able to capture very many different kinds of deployment. So the more you manage to capture, the better. But in doing this, you need a lot of data. And of course, you need to capture different conditions of the environment, different kinds of mobility, different traffic, and also you would need to capture a scale large enough to be representative of what a real deployment might be. So with many base stations and many users. The problem in doing this is that the telecom operator have the data. So they have all the service data of the users and all the historic data of their service, but they're not willing to share this kind of data. And they're not willing to share this kind of data because they fear competition with other telecom operator, for instance. Or another reason might be that there are privacy concerns because this data contain real traffic requests and data exchange or served to the users. So the operator just are not willing to share this data. So we said that we need a lot of data, but the operators that have this data are not willing to share. So how can we do? So one thing is that we need what's called open wireless data factories. And these open wireless data factories are test beds that are able to capture very different deployment for testing and training of machine learning solutions. But they're also open not only to the telecom operator to use, but also to researchers that want to develop machine learning applications or optimization application to the network and need to gather huge amounts of data. So at the end, we need some large-scale testbeds to achieve all this. So fortunately, we have Colosseum, which is the world's largest wireless network emulator. So Colosseum is basically a huge data center, as you can see from the picture on this slide. And this huge data center has servers that researchers and users can leverage to deploy open source applications. So for example, a cellular stack, or Wi-Fi stack, so on and so forth. And they can control real radios that are, in this case, USRP X310 software-defined radios. And the radios interact through wireless channel emulator that is able to capture and reproduce different deployments. So you basically can instantiate your application on a general purpose server and control a white box radio that is a software-defined radio in this case. And then the radios will communicate going through wireless channel emulator able to capture different deployments. So for instance, you can capture and test your solution on a urban deployment, a rural deployment, or other kinds of deployment. And basically you can do this without the need to go and ask data to a telecom operator. So what we've done is that we have deployed an ORAN compliant network on Colosseum. So this is a diagram on our deployment. So if you see on the right, we have no real-time rig that has been deployed on one of Colosseum servers. And this component is in charge of the offline training of the model from statistics collected from the radios of Colosseum. So we run a cellular network with real radio devices on Colosseum, and we collect data. At that point, the no real-time rig can train our models offline. And also this component takes care of storing the models that have been already trained on actual data. Then we have a near real-time component that has been deployed on another server of Colosseum. This component runs the XApps that I was mentioning earlier that are in charge of doing the actual optimization and running the actual intelligence. They're able to interact with the remaining ecosystem of the near real-time rig. So for instance, we have components that are managing the connections with the base station through the E2 interface. We have a database inside the rig that keeps a record of the connected base station. And finally, we have actual interfaces that can communicate with our cellular base station. Inside these XApps, we deploy some deep reinforcement learning agents that are made of a fully connected neural network. And they've been trained offline on approximately 6 gigabytes of data in different deployments emulated through the Colosseum channel emulator. And these XApps, what they do, they observe the performance of the network, so the actual real-time performance, so what's going on basically, and they make decisions on scheduling policies or slicing policies for each slice of our base stations. Then we deployed some base stations, and this is the final piece of our network. Base stations have been deployed on servers of Colosseum, so one base station per server. And these base stations have been deployed through our scope framework that I will mention later on. And they are able to interface with the rig and ultimately with the XApps that are running the intelligence of the network. The base station implement different with different services, and they can tune the scheduling policy per each of these slices. And they serve approximately 10 users each, divided in the 3 slices of the network. So we've been running this setup with the goal of optimizing for the mobile broadband slice the throughput of the network, or to maximize the resources allocated to the ultra low latency slices. And we can see that by running closed loop control loops where the actual applications receive data from the users, we're able to achieve significant performance improvement with respect to static policies that here are called RR for round robin, PF for proportional fairness scheduler, or water filling for the water filling schedule, that's WF. And basically our solution is able to intelligently select and switch among these static policies we're comparing our solution with, and to choose the best one for each situation, so each kind of environment we're in, or traffic demand we receive from the user. So another work that I would like to mention is a work on zero-touch optimization of cellular networks. So this work is called CellOS. And the aim of this work was to develop a framework that is able to programmatically control the network based on some high-level intent of the operator. So this framework, to do so, provides some abstractions of lower level network details. So you can think of them as the structure of the network, so the number of base stations or the number of users. And it hides the implementation of the actual intelligence from the telecom operator, that they don't need to know the intelligence part or the optimization theory, but they can simply express a control through a high-level APIs, and then this gets converted into a problem that runs on the network and optimizes. So at a high level, if you remember the example I was doing earlier, we have an operator expresses some high-level intent, and this high-level intent gets passed to the CellOS component that runs this distributed problem and recognizes the intent of the network operator, and is able to adapt to the network state and traffic demand to achieve the network goal of the operator. That might be to maximize the throughput for certain users, or minimize the power consumption for others. More in details, the architecture, first of all of this begins with the operator expressing an intent at a high level for each one of the slices. So you might have one slice where you want to maximize the throughput, another slice where you want to minimize the power. The operator expresses this intent, and this intent first is interpreted by CellOS and converted into a centralized version of the optimization problem that is required to solve this intent. The intent is specified through some high-level APIs, and here you can observe an example of the simplicity of such APIs, where the operator just needs to tell how many base stations there are to control, and the objective level at a high level. So for instance, the line 4, you have minimum power on slice 0. And then you might specify other parameters like the actual optimization technique you want to utilize. After the problem is interpreted, and a centralized problem is formed based on an abstraction of the network at a high level. And then this centralized problem is decomposed into many distributed problems that can run on each network element. So for instance, on each base station in this case, or even further on each slice of each base station. At this time, we still don't know the specifics of the network. So how many users we're serving, or their requirements of throughput and data. but the problem is still general and gets dispatched to our network elements. And the network elements run this optimization problem. And since the network elements know what's actually going on in the network, so the channel conditions, how many users we're serving, and the traffic demand of each user, they're able to specialize this general problem and refine it to the actual network condition and behavior that is going on in the network. And they solve the problem to achieve the final goal expressed at a high level through simple APIs by the network operator. We have prototyped this on real radio devices. So we've been using USRP's B210 that are like the little brother of the X310 that we use on Colosseum. We've been testing this with real cellular phones, and by using open source cellular stacks like the ones that were mentioned earlier, like OpenAir Interface and SRSLT. And we've been instantiating such protocol stacks on general purpose servers, and then they control the network and the radios to achieve our network goal that has been expressed at a high level. We've been implementing all of these in our Arena testbed. This is a testbed we have in our laboratory here. And this testbed is composed of 12 general servers that control a grid of 24 software-defined radios for a total of 64 antennas mounted on the ceiling of an indoor office space. Some of the intent we've tried to pass to CellOS are rate maximization, so maximize the throughput of my network, as you can see in the image on the left, where we have a significant gain with respect to not using our CellOS solution. So if you see, we have a 75% gain from the red line, which is the baseline where we don't use CellOS, and the blue line where we actually use CellOS to maximize the network. Or on the right, you can see a problem of power minimization, which is another problem that we've tested. And even in this case, we are able to reach decent performance of the network while minimizing the power and controlling the power for reduced interference among the various base stations. We also try to program different control objectives on different network slices. So on slice 1, a rate maximization problem, and on slice 2 of the same base station, a rate minimization problem. And we've noticed that we're able to achieve both goals on the same base station, but on different network slices, of course, at the same time. So the operator might have one service expressing some requirements and another service on a different slice, which has totally different requirements. And with this, so this solution is adaptive enough to be able to reach both goals and to adapt to the conditions of the actual environment. Even further, we've been testing this on the Powder Renew platform, which is an outdoor city scale platform that is in Salt Lake City, Utah. And even though the performance are different, let's say the performance reached by the user is lower than what we experienced in a laboratory setup. Mainly because here we have real distance, like distances similar to what a real deployment could have. So we have users hundreds of meters away from the base station. We still see that we have an advantage in running our CellOS solution with respect to the baseline situation where we don't run this application. After doing this, that runs traditional optimization techniques, we've made a version of CellOS that uses machine learning to optimize the network instead of traditional optimization. And this is because with traditional optimization, it might be hard to achieve to have exact equations to achieve a certain goal in an efficient way. So we tried doing a machine learning approach, and we call this QCell because we use DQ networks. And the way QCell runs is that we have distributed agents running on each base station. The agents will receive some performance data from the network, similarly to CellOS, and then they will determine some optimized solution for that specific instant of time. And then they will exchange some signaling information to the other base stations to let them know which actions they are taking. So they can specialize even further the control actions to send to the base station. And to test this, we have prototyped this on Colosseum through the scope framework that I will talk to you later on. And we've tested this on 3 base station and 22 users in a scenario mimicking a Boston common garden, which is a park here in Boston scenario. So we can notice from the results that we've collected that during the initial training phases, we have a loss that is initially high, but then the loss starts decreasing as the training proceeds. And similar happens to the reward, which starts increasing until at an acceptable level of convergence. And then we have our testing phase, that is the last figure on the right, where we can notice that after we train our solution and we deploy that on a different scenario in the network, we're able to achieve almost 40% increase in the user throughput with respect to the best performing scenario without using our QCell solution. So this would be the green line where we use QCell against the blue and red lines that are the best performing experiment without using QCell and an average of all the experiments we've been running without QCell. So I've been mentioning all these cellular network implementations and this scope framework a few times as of now. So I would like to talk to you about this framework that we've been developing to do prototyping of open and softwarized cellular networks at scale. And we've been releasing we've released this framework openly to anybody. The code is on GitHub at the repository here on the slide. But also, if you're familiar with Colosseum, we have an instance of scope that can be easily started and used by Colosseum users. So I've been telling you that cellular networks will be even more softwarized in the years to come. And I've been talking about softwarization and virtualization a lot. And I've been telling you that we will be able to deploy custom services on demand on general hardware and to program the network functionalities in software without the need to actually replace the whole piece of equipment of the network. And of course, to also optimize the network performance through closed control loops, either from a centralized perspective, like the ORAN solution I was mentioning earlier that was using XApps, or even in a distributed way through frameworks like CellOS, which is running traditional optimization techniques, or even QCell, which is CellOS with machine learning inside, let's say. So AI-enabled CellOS. But to do so, we need some research tools that are that we can use to prototype such solutions in a controlled environment. So we need some cellular stacks, so some piece of software that we can deploy on the hardware, and then this software takes care of implementing our base stations on user applications. So we can actually connect all of these frameworks that we develop, like machine learning, optimization frameworks, so on and so forth, so that we can connect these frameworks to the actual 3GPP compliant cellular stack, which drives real world radios and allows us to test our performance on real hardware devices. Also, as I was mentioning before, we need large-scale data set to design and train machine learning and artificial intelligence solutions. So Scope is a solution that we've been developing in the lab for a few years. And initially, Scope was just for our internal use. So whenever we had to test some solution like the Cellular solution or the QCell solution, or even the ORAN-based optimization through XApps, we had to we had the need of some protocol stack that we could reconfigure based on our needs. So this is the reason why we started to design this Scope framework. And this Scope framework allows users to modify the slicing functionalities of the network. So you can allocate more resources to a certain slice and fewer resources to another slice. It allows you to play with the MAC layer functionality of the base station. So for instance, you might implement custom scheduling policies other than the ones provided with the baseline cellular implementation, which in the case of Scope is SRS run. Or even you might need to do some physical layer modification to control the modulation encoding scheme or the power control. For instance, if you want to optimize the power, as I was doing with Cellular. Also, Scope not only allows you to play with the functionalities of the network and to dynamically reconfigure the network in real time based on some intelligence that runs in external frameworks like ORAN or CellOS or QCell. But Scope also allows you to automatically collect data from the run statistics. So you have some run experiment going on, and Scope automatically collects data for you and packages all these data into data sets that you can then use to train your machine learning solutions, or even to perform prototyping of solutions and debugging. So maybe you want to figure out what's going on. You can dive into these metrics data set that Scope provides. To be able to use Scope from external frameworks, Scope implements some flexible high-level APIs that you can use to control the run in real time. So for instance, there are APIs for scheduling reconfiguration, and there are APIs for network slicing configuration or for the configuration of physical layer parameters that the framework I was mentioning before can connect to modify the configuration of the base station in a real time without the need to actually restart the whole base stations and users. So as an example, the ORAN XApps I was talking about earlier was doing scheduling and slicing optimization. So after receiving the data of the actual run performance from the Scope framework, the XApp would process this data and find out some control action to pass to the base station. So for instance, a control action might be for slice 1, change the scheduling policy from a round robin scheduling to a water filling scheduling policy, and also allocate a little bit more resources to this slice because maybe traffic demand is increasing for that slice. So in this case, the XApp that generates all of these directives needs to be able to communicate these directives to Scope. And this is done through these APIs that the XApp can talk to, and they allow to implement the needed control. So for instance, change the scheduling policy of the base station, or modify these license resources for the base station. And Also, all of these scope has been designed through LXC containers that are containers similar to Docker containers, if you are familiar with Docker, and they allow you to swiftly move your application from one piece of infrastructure to the other, so in between different servers, or even between different test beds without the need to reconfigure from scratch your whole application. So this is for increased repeatability of experiments and portability. And finally, scope, since it's implemented through Colosseum, enables you to prototype custom solutions at a scale. So using the Colosseum scale, which is that of 128 software-defined radios that are usable by users of the testbed. So just to give you an example of what scope can achieve, scope can achieve, can facilitate the experimental process from a user perspective. So for instance, without scope, if you want to run some experiment like the ones I was mentioning before, so for instance, start several base station and users and run some control framework that optimizes the performance on my network. If you want to do that without scope, this might take several hours, and you need to set up manually every single piece of equipment. So every server, every base station, every radio, and also you need to manually run every experiment. So this might be really a time-consuming task, and it might take several hours or even several days to achieve a whole experimental cycle. On the other hand, with scope, you can configure a container once, because as I was mentioning, scope is built over LXC containers. So it means scope is nicely packaged into a container that you configure one, and then you can easily deploy multiple times on your different servers. And also you have that Colosseum allows to automatically run bulks of experiments through a simple interface. So you just choose which experiments you want to run. You configure your experiment beforehand to actually do whatever you want your experiment to do. So for instance, instantiate a cellular network, monitor my network performance, and if certain conditions apply, like for instance, my throughput is lower than what is required by my users, optimize my network in a way that I can satisfy the requirements of the users. And all of these can be run automatically by Colosseum through single CLI commands, and it can run at scale on many servers. So for instance, in the initial example of ORAN I was mentioning at the beginning of my presentation, we ran scope on something like 50 nodes. Some of them were base stations, some of them were users, but in all of these, we had to configure scope only once, and then Colosseum facilitated a lot the task of performing the actual experiment in bulk. This also allows you to easily collect data from the network, because you can set up the experiment once and then run it multiple times on different scenarios. And you only need to specify, the only difference you need to specify is the actual scenario. So for instance, the first time you specify urban scenario, you run it several times, and then you just need to change urban from urban to rural. That is literally a numeric string that corresponds to the emulation environment. And you can have Colosseum running your experiment automatically, and then data will be saved, and after the experiment is done, and you can collect this data for debugging or for training of your solution. On another hand, without scope, I cannot really imagine running a data collection at scale on 50 different nodes for something like 70 cumulative hours of experiment. I would say that this might take weeks or even months to do without using scope and Colosseum. So as an example of what we've been using Colosseum for, you can emulate a scenario like we have a Rome downtown scenario on Colosseum that actually mimics the positions of real world deployments of base stations that have been taken from an open source database. And the base stations here are the blue circles with the number. And we deployed softwarized base stations and users. And we evaluated the performance of the network. As you can see, we not only can emulate the scenario, but we can also emulate some external interference, which is external in the sense that it's not really external, but we implement some additional interference to what we normally would have. So for instance, the purple and blue lines on the bottom have this kind of interference, and you can see that they perform differently from the red and orange curves. So Colosseum allows us to do all of this by means of using emulation scenarios. So with Colosseum, it's easy enough to choose a scenario, deploy the network, and evaluate performance. To do the same without Colosseum, we would need to go on site with actual radio equipment. And you might be able to do that with maybe a handful of radios and computers, like 2 or 3. But I don't think there's any way anybody can do that with 50 radio nodes and high performance servers. Also, other than going on site, even if you go on site with some radios, you might experience different conditions based on the hour of the day, the weather. So the outcome of your experiment might not be repeatable as is on Colosseum, but it might actually vary based on if you're doing the experiment maybe during the day where there are a lot of cars going around, or at night where it's quieter and fewer cars and people are in the environment. As an example of what we provide with Scope, we provide this environment, which is, let's say, a plain environment that users can customize, and in the sense that they can get the plain Scope environment from Colosseum or from our GitHub repository and modify it to have additional logic inside Scope. So for instance, I designed a QCell solution that I was mentioning before. And what I would do when testing this solution is that I would get my Scope container, I would install QCell in my container and have my QCell container talking with the Scope APIs to exchange data performance from the cellular network and for QCell to be able to send my control direction, so modify the scheduling or the slicing of the network. After this has been done, the users of Colosseum can select the radio frequency scenario, so which wireless scenario to emulate, and also which traffic scenario to emulate on Colosseum, which regulates the traffic my users and base stations are exchanging. And after that, they just run the Scope modified version of Scope, so the Scope plain Scope that they modify with external logic that talks to the Scope APIs, that they can just run it several times on Colosseum to collect data and prototype their solution at scale. And at the end of this, they can also save these metrics for online processing or the creation of customized data sets. I was mentioning all of these emulation scenarios. So with Scope, we also design some cellular scenarios where we can specify various parameters like channel condition, location of base station and users, the mobility of the users, or regarding the traffic, the type of service of the user, like URLC, EMBB, or MTC kind of service, our traffic flows and direction, bitrate, or traffic distribution. And basically, we can test the same solutions just on different scenarios, only changing the scenario we're running, but keeping the rest all the same. So there's no need to reconfigure all the cellular infrastructure, the intelligence part, but only to choose different numbers for the scenario, both the frequency, radio frequency scenario and the traffic scenario. An example of the scenarios we've been implementing is the scenario of Rome, Italy, I was showing in a couple of slides back, a Boston scenario, and also a Salt Lake City scenario, which corresponds to the actual deployment of the powder testbed in Salt Lake City, which is the city scale testbed I was mentioning earlier. And the goal of all this is not only to design reliable solutions and to prototype them on Colosseum, but ultimately after you design and prototype solutions on Colosseum, you can port these containerized solutions, so for instance, scope with your added intelligence and optimization routines that you developed on different testbeds. So the idea is that you first prototype your solution on Colosseum at a scale using as many nodes as possible. Once you're happy with how your solution performs, and you finish your prototyping phase, you can validate your solution on a real-world environment like the Arena testbed I showed you before. That is a real environment in a laboratory setup. And once you're happy with this, you can test it at scale in the city scale platforms of the Platform for Advanced Wireless Research Programs. For instance, the Powder platform I was mentioning. We've done all this. So we prototyped first on Colosseum, that is the blue line here, tested on Arena, which is the red line, and tested then finally on a city scale setup on Powder. And although we can see that performance are not exactly the same, and this is mainly due to the different environments that we have, because let's remember that Colosseum is an emulated environment, while Arena is an actual wireless environment with people going around and the channel changing constantly. And finally, Powder is a city scale setup where the distance of the nodes is not just few meters, but it's actual hundreds of meters. The behavior of the solution prototype first on Colosseum and then tested on real testbeds is consistent with one another. And just to conclude this talk, we've seen that data-driven solutions allow you to improve the performance of the network, and they can implement it in the Open Run. So for instance, in the ORAN framework. And although they allow you to improve the performance of the network, they require a really huge amount of data to be effectively tested on different solutions. And so then they are able to generalize to different situations. And so we have a need for open wireless data factory, such as Colosseum. Then we've seen zero-touch distributed optimization, where we have solutions that can be swiftly deployed by the cellular operator, and the cellular operator can specify some high-level intent, so maximize throughput, minimize power, and also slice-dependent intent, and they don't need to know any details of the underlying implementation of the network or of the optimization theory behind this. And this means that even anybody with a lot of expertise on these various fields can operate these frameworks that allow you to achieve real-time self-optimization of the cellular network based on your final goal and performance. And they are able to do so while adapting to ever-changing network traffic and conditions. And finally, I showed you scope that allows you to do prototyping at scale for NextG cellular networks. And I believe the scope truly facilitates the design and prototyping and testing of solution at scale, even more if scope is used together with Colosseum. And to facilitate all these data-driven and machine learning routines, scope also allows you to automatically collect data from the performance of the run. So basically from what's going on in the run. And I think these are great resources for 5G open software. So this is kind of a self-advertisement spot. So we have a survey on open programmable virtualized network. And if you would like to know more on this, I would suggest you to have a look at this survey. And then we also have we're together a website that is open5g.info that is a resource that people in the community can contribute to keep a central database of software for cellular networks. So for instance, for the radio access network, for the core network, RAM frameworks, and so on and so forth. Finally, for the self-advertisement part, we are organizing an event that is called Open 5G Forum, and it's going to happen November 17 and 18. And this is a virtual event, and we're sponsored by the ACM SIG Mobile Group. And this event hosts various people from open source projects on the run, because this is the run edition. We will have a core edition next year. And basically we invited people from these open source projects to come and tell us more about how these projects work. Like we have people from Open Interface, from SRS-LT, but we also have people from the Open Networking Foundation talking about the softwarization efforts of cellular networks, and we also have various panels with industry members. And all of this with a focus on Colosseum. So for instance, the solutions that we're showing will be also showcased on Colosseum. So if you'd like to know more, this is the link to the program. So it's Open5G info /Open5G forum. And I would encourage you to have a look at these if you're interested in this event to register. Registration is free, but is required to have a sense of how many people will be participating. With this, I conclude my presentation. I thank you very much for your attention. If you have any questions on this, I would be happy to answer those.